Hi everyone. So this is the video for your second party, midterm number 2, which is scheduled on Wednesday, this coming Wednesday, April 8th. So let's talk about, first of all, let's talk about the, um, the information about the exam, the schedule and the topics and some logistics issues. Okay, here we go. Here we have party number 2, also known as midterm number 2. Schedule is, I said, April 8th, which is a Wednesday during our class time. So it's going to be 2:30 to 3:30 p.m. Of course, this is the Pacific time on Wednesday, April 8th. Okay. So what I'm going to do, I'm going to post the test on the Blackboard during this time, and I'm going to add 15 minutes at the end. And this 15 minutes is the time that you are going to take a picture for all of your work and convert that picture files into the one PDF file. So what you need to do is you have to download the app on your cell phone, and there are a lot of different kinds of app to convert the pictures into the PDF scanner, or just convert picture to PDF. You can search it and you can see a series of the applications available. So take pictures of your work and then convert all those pictures into one PDF file and upload it onto the Blackboard. So that's this additional 15 minutes. So what I'm going to do is I'm going to make that test on the Blackboard page available between 2:30 to 3:45, right? So you're going to take 1 hour exam during this 2:30 to 3:30, and then that last 15 minutes during that time, you're going to convert your work into one PDF file so that you can post it on the Blackboard. All right, this is open book, open note, open whatever material that you have. So you don't need to make a formula sheet this time, and any materials is going to be available, but communication between your classmates is not allowed, right? So I'm going to put the academic dishonesty, the academic integrity rule captured from our syllabus. That's the top of your midterm number 2, so that we're going to still follow that rule. Open book, open note, and you can have your calculator ready. And what else? This test will cover chapter 10, 11, and 15. So I'm going to go over each chapter one by one. What are those, the key informations in which example problems that you need to cover and exercise to prepare this midterm exam. Okay, so I'm gonna just clear and change the color. So let's start with chapter 10. So chapter 10 is about torsion, and this is only for the circular shaft. So we already studied this in the class. What if we have a torque T, and in this chapter we studied several different things. So first of all, we should be able to find out the stress according to this torque, and that is the shear stress. So let's say this is the cross section of this circular shaft. Here is the center, and we can measure the radial distance starting from the center, that is called the rho. So this tau, the shear stress at a certain location with this radial distance rho from the center, we can calculate it as T, the torque, amount of the torque here, times the rho, that radial distance from the center, divided by J. And this J is the polar moment of inertia. For the circular solid section, it is pi over 2 times the C to the 4th. C is the radius. This is C, okay? When you have a hollow section, like there's a hole inside of it, then we can measure two different radii, the outer radius and the inner radius, right? So you can calculate the J as pi over 2, CO, that is the outer radius, 4th, minus CI, inner radius, to the 4th. So anyway, these polar moment of inertia will tell us the rigidity of your section against the torque. Okay, so that's how we can calculate this tau, and the maximum value of tau is this T times C over J. So T and J's are kind of constant and given. We can, this rho is the only variable, so this rho can vary from 0 to maximum value of rho, which is going to be C. So that's how we can maximize this rho to get the maximum stress tau max. We also talk about angle of twist phi factor. So let's say this is the original position. Due to the torque, we have an angle change that is called phi. So angle of twist phi is equal to T, torque, L, the length of the shaft, divided by J, the polar moment of inertia. Here's the equation. And G is the shear modulus of rigidity. So this is very kind of comparable to our sigma equation. The delta equation, due to the actual force. Delta was equal to P L over A E. So P is comparable to the torque here as a given load, L the same, and A and J, those are the kind of rigidity, and GE, those are the material properties, the Young's modulus and shear modulus. So this is the equation how we can calculate the amount of the deformation, the angular deformation due to the given torque T. All right, and this equation is actually used in to solve the statically determinate problem. The indeterminate, sorry. All right, so here we go. Statically indeterminate problem, which means we cannot figure out all the reactions or the internal forces with a given amount, a given number of the equilibrium equations. The equilibrium equations for 2D analysis, we always have 3 equilibrium equations available. What if we have more than 3 unknowns? Then that is called a statically indeterminate problem. In any cases, the statically indeterminate problem, if we can find out the deformation information, then we can have that as additional information to solve the unknown. So let's say if we have 4 unknowns, then 3 can be determined using the 3 equilibrium equations, and this one, which requires additional information. And this phi angle can be used to solve the statically indeterminate problem. And later this chapter, we also talk about the power transmission. And this power P can be calculated as torque T times omega, which is angular velocity. The unit for this angular velocity is radian per second, okay? And also this angular velocity can be expressed in terms of the frequency, which is 2 times pi times f. So this P can be expressed in terms of f as well, which is 2 times pi times f, the frequency, and then multiply by t again. So think about the unit for the power P. Many times we use watt unit in SI unit system, which is equivalent to Newton times meter per second. So in the SI unit system, we have pound feet over second unit. But also we have a horsepower unit can be used to express the amount of the power, okay? And there are the conversion factors, so you can make those conversion factors available. All right, so these are the main topics and main concept in chapter 10. And there are several the example problems. So examples 10.1, 10.2, 10.5, 10.6, and 10.8. So these are going to be good exercise problems to prepare this chapter 10. And you also have entertainment package problems, right? Problems available. Okay, so this is the quick summary of chapter 10. Let's go over to chapter 11. So chapter 11 is mainly about the bending moment and the beam bending and the bending stress. So in chapter 11, the main topic at the beginning was the shear force diagram and bending moment diagram. So we spent a lot of time actually and went over the most of the example problems in the textbook to exercise this. So shear force and bending moment. So let's say here we have a simply supported beam under a certain transverse loading. Then typically we have a shear force and bending moments due to this load. So that's how we develop the shear force diagram and bending moment diagram here. So the relationship is this. This intensity of the load is W. It looks like a omega. So it's W. And then the shear force is V. Bending moment is M. And we look at the relationship among these three quantities. So this is the intensity of the load, shear force, and bending moment. And the relationship is when you do the integration from the load to the shear and shear to the moment, and the backward is derivative relationship. And in math, integration means the area, and this derivative means the slope, right? So using this graphical, the relationship, using this relationship in the graphical method, we should be able to develop the shear force diagram and bending moment diagram easily. So the several example problems in your textbooks are going to be a good exercise problem. 11.5, 11.6, 11.7, and 11.8. These four problems could be a good exercise to develop the shear force and bending moment diagram. And one of the reasons that we develop these diagrams is to identify the maximum value, because as an engineer, we're always looking for and interested in finding out the maximum value of a certain quantity. So that's how we can identify not only just the distribution of the shear forces and bending moment all over the length of the beam, but also we can easily identify the maximum value from there. So using this relationship, we should be able to find out the shear forces. So area under the load is becoming the change in shear. Area under the shear force will become the change in bending moment, and vice versa. So when you look at the slope on your bending moment diagram, that should be equal to the value on your shear force diagram. Slope on your shear force is going to be the intensity of your load. So we have that. When you have concentrated forces or concentrated moment, you will have a direct jump on your shear force diagram and the bending moment diagram. And one thing I emphasize it is clockwise moment. This is different from the sign convention of our bending moment. Clockwise moment will create a positive jump. Counterclockwise moment will create a negative jump. That this is the only difference and kind of opposite to our sign convention of the bending moment in the universal sign, based on the universal sign convention. We also talk about in chapter 11 how we can figure out the actual stress due to the bending moment. So the typical equation is this my over I. So sigma is a bending stress. So this is called the flexure formula. So bending stress is equal to negative sign of m, the bending moment. Y is the vertical distance. So let's say this is the cross section of this beam, and here we have the neutral axis, and y is this vertical distance measuring from the neutral axis, and I is the moment of inertia. So let's say B and I, the rectangular shape, I is simply BH cubed over 12, and moment is directly coming from bending moment diagram. And the reason that we put the negative sign intentionally is because think about the positive moment. Positive moment, under the positive, remember the sign convention? Smiling face and the sad face, right? So this is the sign convention for the bending moment. This is the deflected shape when we apply the positive moment. And under the negative moment, this is going to be the deflected shape under negative moment. So under the positive moment, we will have tension on the bottom. So tensile stress is going to be developed in the bottom of the section, while the top portion is going to be in compression. Under the negative moment is going to be opposite. We will have a tensile stress on top and compressive stress on the bottom. So let's say under the positive moment, to become the negative stress on top above this neutral axis, because that's where this y value is going to be positive, and below this neutral axis, y value is going to be negative. To make this, signs matched, so under the positive moment with the positive value of y, we have to have a compressive stress, which will be the negative sign of the stress. That's why we intentionally put this negative sign in the formula to match that sign convention. Okay, the other expression is for the sigma max. So when you maximize this y value from here to the top or the bottom, that is called MC. So C is going to be the maximum value of y divided by I. And this I, here we have C over I, and I over C is defined as the section modulus called S value. So M over S will be equal to sigma max. And this equation was used in the chapter 11, right? Okay, so I think this is everything from chapter 11, and as I mentioned, these 4 problems for the shear force and bending moment diagram, and then I'm gonna add 11.9 and 11.11 for calculating these bending stresses. Oh, one thing, 11.5, section 11.5 will not be included in this time of the exam. This is unsymmetric bending. We're gonna cover this only in the final exam because of the time limit. So you don't need to study 11.5 for this time. Okay, 11.5 will not be covered this time. All right. Okay, so let's go over chapter 15. Chapter 15 is about the design of the bending members. And the reason that I covered chapter 15 right after chapter 11 was because the topics are related. So in chapter 15, so earlier chapter we talked about sigma max was equal to MC over I, where I over C is called section modulus S. Then we can say this is equal to M over S. From there, this sigma max in the design problem, this is going to be the allowable stress, which is coming from the maximum either compressed stress, or compressive stress or the tensile stress from the material testing, then what we can do is this M is going to be the maximum value of the moment to make sure that our section, the selected member, is going to be strong enough to hold that moment. Then we can rewrite this equation as this: the S required will be equal to M max divided by sigma allowable. Okay, so the sigma allowable is going to be the material properties coming from the material testing, and this M max is coming from the bending moment diagram. So using these two values, you should be able to find out the sigma required so that you can select the section. And we had a practice that was an example 15.1. Remember the table of the W shape section, W12, W10, W8. So we find out the required section based on this S value, and then pick the lightest one among those candidates. So example 11, the 15.1 would be the good exercise problem for 15. And that's it. So chapter 15 is pretty kind of straightforward. If you're familiar with this example 15.1, how to find out the lightest section based on the candidates. And of course, you have to be able to find out the maximum moment from the bending moment diagram, and to calculate this S required value, how to read that chart. And that chart is available in your textbook, right? And this is an open book test. I'm not going to provide the table for you, but you can have it handy during the test. So these are the problems and the topics and the equations that you have to understand. And if you're familiar with this entertainment package problems and the example problems that I just mentioned during this video, if you want, you can go over the PowerPoint slide as well. But I think that should be enough to be good in this exam. All right, so this is all. Thank you very much, and see you on Wednesday.